clear the ink. Okay. We are in section 2.4. I believe at the very beginning of page 76, using elementary matrices, right? Example 3. Okay. It says find a sequence of elementary matrices. Oh yeah, I'm sorry. All right. Yeah. Sequence of elementary matrices that can be used to write matrix A in row echelon form. Okay? So, and I'll admit right up front, it seems like we're going around our elbow to get to our ear, but this is what's happening. Exactly. I got it. Good deal. Okay. Here's matrix A. 0, 1, 3, 5. 1, negative 3, 0, 2. And 2, negative 6, 2, 0.
So is there a point to doing it this way versus our normal way? Like, is there any advantages, or is this advantageous for the future?
For the future. You have to get that in there. Right now it is
useless.
It is doing the same work twice as long almost. Okay. It's for future prospects that it comes into play. And we'll almost get to that, but you still won't see what the real advantage is. But what. Okay, now, what we're going to do, and I sort of like the way the book presents this, except it's real hard to do on a small screen. Okay, what would you do, your first step to get this in row echelon form?
Switch row 2 and row 1.
Okay.
So what we would
do
is take an identity matrix.
Yeah. So let me just do the identity matrix over here. But what size identity matrix would you need to be dealing with?
It has to be a 3 by 3.
3 by 3. You can't do a 3 by 4. There's no such thing. And you don't want the 4, so you do the 3. Okay? And just reminding ourselves what that is. What is it?
1, 0, 0, 0, 1, 0, 0, 0, 1.
Got it.
That however you want.
Okay.
This way, that way.
Now, your first step here was row 1 and row 2 are exchanged. Okay? So we're going to do that here. And that will become 1, negative 3, 0, 2, 0, 1, 3, 5, 2, negative 6, 2, 0. Now, do that same row operation to your identity matrix, and what do you get?
0, 1, 0,
0, 1, 0,
1, 0, 0,
1, 0, 0. I started to, I can't write. Okay. Okay. Now, next step.
You get a 0 for row 2.
Okay. How do you do that?
Double row 1 and add it to row 3.
By minus 2.
Negative 2.
Row 1
Plus
plus row 3. Okay. So that becomes 1, negative 3, 0, 2 stays the same. 0, 1, 3, 5 stays the same. This now becomes,
0, 0,
whoa, nice, huh?
2, negative. That's the way that's turning out so far.
Right. Now, what? Now, here is the thing. On your elementary row matrix side, you always go back to the identity matrix to do this operation. Don't build on the previous one. Just do
So you
the
make a whole new one.
yeah.
Done with the last one.
Right. And by the way, they call this E1. Elementary matrix 1.
So this was E2.
This is E2.
Okay.
And what would it be?
Alright, so it'd be 1, 0, 0, 0, 1, 0.
Wait, okay, yeah. Yeah, 1 0 0 0 1 0. Mine just flipped out on me. Okay. 0 0 negative 2. Right. Okay. Because you do that same. Huh?
This is almost just like a different way to keep log of what you're doing.
Exactly. Yeah, you can think of it exactly that way. Okay.
So next we want to get a 0 above the 1, or what?
Okay. Wait. I don't think we did that one right. We didn't just multiply the third row by minus 1.
Oh. No,
yeah.
It should have been negative
Yeah.
1, 0, 1, not negative 2. I'm sorry.
Okay.
I got 2 assigned.
Okay. Now wait one. Just what did you say? Oh, I didn't erase enough.
It'd be negative 1.
Wait. I'm not sure that's right either. Wait.
Negative 2.
Okay. I can't get this to erase. Yeah. Okay. Finally. All right.
Negative 2.
-2 0 1. Got it. Okay.
I boxed that all over.
Okay. So that's your E2. Okay.
We can divide that last row by half, or multiply it by half, also be
Okay. Well, you got a couple of things to do. Yeah, and that is the next thing they're going to do too. Now, we're wanting, are we doing row echelon form or reduced?
This is row.
Only row. Okay, yeah. And so the last step is that. Because you're not doing a reduced row echelon form, you're doing the row echelon form, which means divide that by 2. Okay? So that would be, yeah. And so your E3, and I'm running out of room, E3 would be 1 0 0 0 1 0. Okay, got it. Okay, now that has gotten it to row echelon form, and to keep from writing everything again, I'm just going to write that as a 1 and that's a -2. Okay. Okay. Not that we really need that much. Okay. Now, okay. I'm trying to figure out where the best place to erase. I don't need this. I just put it up there for you to always be able to go back and look at, but now we don't need it. We got our 3 matrices. Now, what this has done for us is this. Okay? Let's start with this matrix A and operate on that matrix A with first your E1, then your E2, and then your E3. Okay? And that's matrix multiplication. Okay?
So you got to do it. That's kind of a weird way to write it.
It is.
Times E2 times E1 times A.
Right. But let's start with the A and work backwards on it. Because, I mean, you don't have to, but that's the way that sort of follows. So what I'm going to do then is,
The E's would be kind of quicker.
what's that again?
If you started with the E's and then worked your way in, probably faster. Because you wouldn't be right up the board the whole time. You have a lot of zeros.
Right. They do it the other way. And I don't think it really matters big time, but I think they're wanting to sort of show this. I'm not going to be able to show it because I can't keep it all on here. maybe I can do this. I've been trying to think how to present this on the slide. So I think I will see, again, if I had integrity, I could just loop this and move it. This won't do that, so I got to erase and rewrite. So what we want is E3, E2, E1, A. All right, here's our A. So I'm going to write the A here. Again, I would have just looped it and done 0, 1, 3, 5, 1, negative 3, 0, 2, 2, negative 6, 2, 0. And operate on that with E1, which is 0, 1, 0, 1, 0, 0, 0, 0, 1. And after we do that, then we'll multiply this by E2, which was our 1, 0, 0, 0, 1, 0, negative 2, 0, 1. And then, since I've already written my A down, I'm going to erase the A because I don't need it anymore. But I would like to hang on to the rest of it just a little bit if I could. Okay. This has been trying to figure out the logistics here. 0, 1, 0. Oops, 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 oops. This is 3. I've already done that. Okay. Let me go back. Ha! Sometimes it takes and sometimes it don't. Okay. Okay. 1, 0, 0. 0, 1, 0, 0, 0, 1/2. Okay, that's what we're going to be doing. So now I'll erase these because I've already written them down. I just hope I wrote them right. What's that?
We need to buy more ionizing pens.
Right, yes. I like that one. Okay, now let's multiply these two first. All right, that's going to give us a what?
0.
Yeah, but I mean, what size?
3 by 4.
3 by 4, okay. All right, you don't have to do that. It helps me keep track. What does that give you?
It would be 0 plus a 1 is a 1 for the first blank, right?
Right. Are you going down or right?
Going down.
Down, okay.
And so it would be 0 plus 0 plus 0, 0. 2 below that.
Yep.
2 below that.
2, oh, okay. I thought you were saying, I'm going to do the one below that. Okay. I understand. That's where the way you go. Okay, got it. All right, next.
And then it would be negative 3.
Negative 3. 1.
Negative 6.
Got it.
0, 0. Oh, 3, 2, and then 2, 5, 0.
Got it? Now, what do you notice? When you did the elementary row operation, that's equivalent to multiplying the elementary matrix corresponding to that row operation by the original thing. You get the same thing. Okay? Now we take this one, and so we see that. So now I won't hang. Whoa. Okay. I won't hang on to this any longer because we just reproduced it. But I'm going to take that now and multiply it by this matrix here. Can we just do it like this so I don't have to write it again? Okay. So if we do that, what does that produce?
1,
Okay.
0, -2, +2, 0.
Okay. You're okay. Sorry. Let me get.
Hold on.
Okay.
1, 0, 0, that's 1.
Yeah.
0, 0, 0.
And you're doing below, right?
And 0, 0, 0, yeah.
Okay. And what's the last?
0.
0. Okay.
Next row, column, -3, 1, +6, -6, 0 again.
Okay.
Okay, next row, 0, 3, 2.
Okay.
And the last one, 2.
Okay. Okay. I had something pop up. Okay. Right. 2.
5.
Well. Okay.
And then -4.
Oh wait. Sorry. I was fighting with my thing and didn't get it to be right.
I think 2 was right.
Well, let me go back and see. Okay. All right.
Should be a 2 and a 4 at the bottom.
Okay. Let's. Oh yes, it is. It's a 2 and a 4. I forgot. -4, isn't it?
Yeah.
Yeah. Okay.
And we multiply that by the.
Yeah. And that's the one we had there before, and I erased those two. That's why it was confusing. Okay, so you got that, and then when we multiply this by this one by that one, let's do it up here if we can. Okay, what will that give us?
1, 0, 0. The first row.
Mm-hmm.
And -3, 1, 0. Then 0, 3, 1. And 2, 5. -4.
Yeah. And you wound up with the same result here, and this is what they were calling the B matrix. Here you got the B matrix doing row reduction. Here we got that same B matrix by using the elementary row operations that we had to do the other thing to get them, but you get the same result. Okay? So you say, and why did we do it this way? Because you had to do this to get those, and then you do those again to get the same thing you got just the first time through. But it's just showing you that indeed they are row, they're row equivalent, A and B, the original A, the final B, they're row equivalent, and because you obtain B by performing a sequence of row operations with elementary matrices on A. So, sorry about that. It happened last week that I got the hiccups in this class,
Oh, yeah.
and it feels like they're going to happen again. It's beyond me. Why? Let's see. Okay.
So that's about the most lengthy way to
Yeah.
keep log of what you're doing.
Yeah. But let's see. Here now is another definition of row equivalence. We've had a few before. Row equivalence. Let A and B be M by M matrices. Okay. Matrix B is row equivalent to matrix A when there exists a finite number of elementary matrices and they name them E1, E2, E3, dot, 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 up to EK. Didn't know which of the subscripts they were going to use there, such that the B is equal to E sub K, E sub K minus 1, E sub K minus 2, dot, 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 down to E3, E2, E1, A. You know, whatever, however many there are there, that you can do that. If B can be obtained by multiplying A by a number of finite number of elementary matrices, then A and B are row equivalent. We knew that from before, much easier than that. Okay, well, we didn't know about elementary matrices, but now, when way back in, well, last section 2.3, not all square matrices are invertible. Every elementary matrix, however, is invertible. Moreover, the inverse of an elementary matrix is itself an elementary matrix. So here comes another theorem. That's the definition. Here's a theorem. Okay? Elementary matrices are invertible. Okay? Here's how you state it. If E is an elementary matrix,
Inverted matrix. That's where we augment it with the identity matrix, right?
what's that? Yeah, right. Exactly. Then E inverse, if E is an elementary matrix, it is invertible. E inverse exists and is an elementary matrix. Okay? Now, this is step 2 in getting kind of where we need to go. 1 is the first thing. You can do row equivalence that way. Now we're going to do inversive elementary matrices. It isn't, okay? The inverse of elementary matrix is the elementary matrix that converts E back into IN, whatever size that was, okay? For instance, the inverses of the 3 elementary matrices in example 3 that we just did, that I couldn't keep on the screen because I didn't have room enough, but let's go, I was afraid of that. Okay. All right. Here were the 3 elementary matrices we had before. I1 was 0, 1, 0, 1, 0, 0, 0, 0, 1. Now, what was its inverse matrix? E1 inverse. Okay? Amazingly, it's the same thing. It's exactly the same. 0, 1, 0, 1, 0, 0, 0, 0, 1. Yeah. Yeah. And that gets you back to where you started. Okay? So, when you swap 2 rows, you just swap 2 rows. Okay. All right. Okay. Now, the E2 that we had before, was that the, yeah, that was the one that was 1, 0, 0, 0, 1, 0, 2, or minus 2, 0, 1. Okay. Now, E2 inverse, It has to be a matrix that when you multiply it by this matrix, you get the identity matrix again. Okay?
So,
Top root 2 rows, nothing happens basically, so write those down. Okay.
would it be get that third spot?
Okay. So,
I just want to say 1/2.
okay. No, not quite. I was tempted the first time I did this to do the same thing. Okay. Now, imagine you're multiplying these two together. You want to get the identity matrix. So this is going to be a 1 plus 0.
Plus 0.
Yeah. So this thing could be anything because it's going to be a 0. Okay? So it doesn't mean this is a 0. It could be anything. Okay? Then
I think in the second slot in 0, 2 is the
so it's really the third row we're getting at.
Yeah.
We want this to be a 0 here. Okay? So how you do that is 1 plus 0. You need this to be a
I want to say negative 1/2.
no, I want to say a 1/2 because you want that to be a 0. Oh, wait. I'm going the wrong way. Am I? I should be doing this way. I'm sorry. This entry down here we ought to be. So it's this one. Negative 2, right? Plus 0. You got to have a 0 here. Okay. Let's write down what our goal is. Multiply these two together. You want this to be a 1, 0, 0, 0, 1, 0, 0, 0, 1, right? That's I3. Right? So, kind of do it a weird way. You're looking for what element here will make that a 0. Okay?
2.
Yes, a 2 will do it. Exactly. A 2 will do it.
I had to write it in augmented form, but
Right. Oh, okay, yeah.
Because if
You can do it
what
that
you're
way.
doing is you're multiplying to make that a 0.
Right.
It needs to be 2 plus the negative 2.
Exactly.
So it needs to be 2.
Right. Or negative 2 plus 2. And then the next entry,
It'll be 0.
you want that to be a 0, so
And
this
then
will be a 0 plus 0.
Plus 0.
That's got to be a 0 there. Okay.
And then I'm pretty sure the last one will be a 0 as well.
Okay, let's see. You want it to be a 1 ultimately. So you're going to do 0 plus 0. It's got to be a 1. Yeah. So that's what happens there. All right.
That one was kind of confusing me, so I just wrote it
Right.
in augmented.
Right. So let's see what we did. When you're flipping 2 rows, you flip the same 2 rows and you get the same thing. On this one, you were multiplying the top row by negative 2, adding it to the third. Okay? So to undo that, you multiply the top row by a positive 2 and add it to the third. Okay? So you just change the sign of what you're multiplying. Yeah. Okay. And then the third one, the E3 that we had here, was a 1, 0, 0, 0, 1, 0, 0, 0, 1/2, wasn't it? Okay. Now, we want to multiply that by E3 inverse. E3 inverse, I hope,
So the first 2 won't be
yeah, nothing is changing there. Okay.
The bottom row would be
And again, when you multiply these two together, you want this to be a 1, 0, 0, 0, 1, 0. Or you could do augmented, you can do that too. 0, 0, 1.
It would be 0, 0, 2.
It's got to be 0, 0, 2. Okay. Because we do it. Okay. 0, 0. So this is how we undo it. And notice we did one of each. We did exchange two rows, multiple one row plus another row, and then dividing or multiplying a row by something. So that's just the same swap. That one's multiplying by the opposite number and adding, and the last one is multiplying by the reciprocal. So that's how we get our three inverse elementary matrices. I'm trying to think of my words here. All right, that leads to another theorem. Okay, I love these theorems. Okay, I'm going to erase all the ink. I'll probably regret it, but I don't have room. A square matrix A is invertible if and only if. Now there's one symbol for if and only if. IFF is another one, or write out if and only if. It can be written as a product of elementary matrices. Right. It can be written as a product of elementary matrices, or if you can write it as a product of elementary matrices, it can be converted. Okay. It goes both ways. The arrow is both ways, if and only if. If means that way, only if this way. Okay. And that leads them to example 4. I think I'll need the whole space, even though I got a lot of room left here. It's going to take a lot of space. Okay. Even though it's a pretty simple matrix. Here's your matrix A. A pretty simple little matrix. -1, -2, 3, 8. Okay.
So we need to show this as a product of elementary.
Okay, it says find a sequence of elementary matrices whose product is this non-singular matrix. How do we know that's a non-singular matrix?
Shouldn't have zeros at the bottom.
Okay, but you'd have to do row reduction to make sure it didn't. But there's a simpler way since it's a 2 by 2. Huh?
Square.
Yep.
Square.
It's a square, but not all square matrices are non-singular. Remember?
Oh,
Determinant.
Determinant.
Yeah, that would be.
-8.
That's all you need to know. It's not 0. Okay. So it is a non-singular matrix. Okay. So we start by finding the, what we're going to do is not just row echelon form, reduce row echelon form on this one. So what would we do the very first thing?
Invert the row 1, so multiply by -1. Right?
Okay, right. So your first step would be multiply row 1 by -1 is the new row 1. Okay. So the next step would be 1, 2, 3, 8. Which most of the time I would just do it once. Well, what elementary matrices did that?
That would be -1, 0, 0, 1. Right?
Exactly. All right. And while we're doing that, why don't we figure out what its inverse is? what would that be? This would be E1, and this will be E1 inverse.
Be -1.
Negative 1, 0, 0, 1. Okay? All right. Okay. Next step.
Be 2.
I don't know if this is helpful. I'm going to write it up here.
Oh, yeah, this would be easy.
Okay?
So, it would be 3 row 1 plus
Minus 3.
-3 row 1 plus row 2.
Okay? And that would be a 1, 2, 0, 2, isn't it? Okay. Okay, what's the elementary matrix that does that same thing? Negative 3, 1, isn't it? Right? Okay. Because you're multiplying, I wrote the identity matrix, so negative 3, row 1, plus row 2. That gives it. Okay. What would be its inverse matrix? So this is E2. What would be inverse of E2? Sure is what we had last time, isn't it? So let's hope it still works. What now? Okay, or divide by 2, it doesn't matter. It's a new row 2. So this becomes 1, 2, 0, 1. Okay? What's the elementary matrix that does that? 0, 1 half. And what's the inverse of that one?
1, 0, 0, 2.
All right, 1, 0, 0, 2. Okay. And then one more step.
-2, row 3 plus
Row 2, we only got 3 rows.
row 2.
Okay.
I'm adding in rows.
Yes, of course. That's always legal. Yes, okay. And that gives you?
The identity matrix.
All right. So we've got that reduced. E4 here was what?
1, -2, 0, 1.
1, -2, 0, 1. Very good. And E4 inverse.
1, 0, 0, 2.
No.
No?
Doing the wrong. It's. Let's just see if what I wrote works, and then we'll do what you wrote. Okay, this would be 1 plus 0 is 1. 0 plus 0 is 0. 2 minus 2 is 0. And 2. Oops. Oh, that's the wrong one. 0. 1. Yeah. I think that does work. You see, same thing we did here, right? Here, this step, we're coming out this way, we go up that way. Okay. Now, find the sequence of elementary matrices whose product is this non-singular matrix. Okay. Now, since we know that E4 times E3 times E2 times E1 times A is equal to the identity matrix, we know that, right? Okay. Now, how do we get this back to being A?
E4 inverse, E3 inverse.
Yes, let's first multiply by E4 inverse. By that, Of course, we'd have to do E4 inverse here.
Well, what you end up with is A equals each of the inverses times the identity.
Yes. A equal in which order? E4 has to be by I here.
E3, or E1.
Yeah, E1 inverse, E2 inverse, E3 inverse, and E4 inverse. Okay, times I, but yeah, we could leave off the I and just multiply those four together. And it doesn't matter which order. Earlier you were saying you wanted to, now we are. Let's multiply those four together and see if we do get A. Okay, the inverses. Okay, can we do these first two as they sit?
I'm rewriting them.
Okay.
I had to go to a clean sheet of paper.
I know. I probably should, but I'd lose too much.
Alright. So the first two would be -1, 0, or no, 3. -1, 3.
Okay,
We're going down.
down. Okay, 3. Is that what you meant?
Yes.
Okay, all right.
Then 0, 1. Right?
I'm having a mental block here. Okay, that would be.
1 times 0.
Oh, you just did -1 all at once. Okay, got it. Okay, I thought you were adding, and I thought I'm not adding the same thing. What'd you get?
I got 0.
Oh, 0 there. Okay, all right. I thought. Okay. Okay. All right. Let's start over. Okay. Got it. This order here. That would. Yuck. Okay. That would be a -1. That would be a -1 plus 0 is -1. I'll do it your way. If I can get this right.
1 times 0 is 0. And then
0,
0 is 0. So that's
3. Yeah, that's right. Then the next one over would be a 0, 0, yeah.
And,
Oh, I was supposed to have lost that. Okay, 0. And the last one was what?
1.
1. Yeah, okay, got it. Okay, now we're doing these two.
So, the product of those two times
Yeah.
E negative
Okay.
inverse 3 or whatever.
Right. So, all right, with the top one first,
And we wouldn't be able to do this like
you can't
E1
reverse.
and 2 inverse and then E3 and E4 inverse and then multiply their product.
That would be okay too. Yeah, I think so. Yeah, these are commutative. So yeah. I mean, not commutative, associative.
Yes.
Yeah, they're associative, not commutative. Okay, let's.
Kind of what I'm going to do.
Yeah.
E3 inverse times E4 inverse.
You want to do that one next?
Yeah.
Okay. Let me find my eraser and go back and do it. Okay. We'll do these two. We'll multiply these two together. Can I write it below it?
Yeah.
No, I think I'd rather write it over here. Okay. Let me write it over here. 1, 2, 3, 4. Okay. That would be 1 plus 0 is 1, right?
And then
You do second, you do 0, that's a 0, right?
right.
Okay. Then you do, I can't read, that is a 0 up there, isn't it?
And then it's a 2 and a 1.
2. That is a 0 up there, right? Oh, you mean a 2 and a 1 here. Okay, right, okay. I thought you were adding those, okay.
Now we can multiply those two.
Those two together, and what do we get here? We'll do this times that. And that would be a -1. You got a 3, you said?
Yep, -2 and 6, 7.
Second?
7.
No, it's not 7, I don't think. But
Did I leave off the sign?
wait, I was misunderstanding. I got behind where you were. So let me get this back again. Have I got, yeah. All right, okay. That's a -1. Yeah, that's fine. 3's fine. Then you had -2. Yeah, that's fine. And then this should be 6. Okay, something's wrong here.
Oh, because they got 8, didn't they?
Yeah, it's supposed to be an 8. And that's where I was trying to find my error. So close. Okay.
Well, let's go back to the multiplication. 1, 0, 2, 2. That one there, the middle.
Yeah,
the
3
1,
times
2,
4.
No, the 1, 2, 0, 1.
Yeah.
That last one should be a 2.
Yeah, that's what I thought. That should be a 2. Okay.
And then that'll make that an 8, and then there we go. Hunky-dory.
8. Yeah. That's what I thought was the error there. Okay.
We found it pretty quick, so
Yeah.
that's good.
Excellent. Okay. So sure enough, we did find that this invertible matrix, we determined that was an invertible matrix, is a product of elementary matrices. Now, those elementary matrices happen to be the inverse matrices, which are also elementary. Inverse of the elementary matrix is an elementary matrix, and it would be the one that got you down here in the first place.
See,
Now,
when I first read the theorem, it
Yeah.
said the square matrix A is invertible if and only if it can be written as the product of elementary matrices.
Right.
I was thinking to myself, the product of 2 elementary
No.
matrices, and I was like, how is that going to work?
No.
It's just multiple
Yeah.
products.
they left off the number there of as many as it needs. Okay. All right.
Theorem.
Next theorem. Now, these are some equivalent conditions, and these theorems build on each other. Okay? Big time. We'll start now, and we'll keep adding to it, I think. Okay? And here it is, equivalent conditions. If A has to be square, n by n matrix. Okay? Then the following statements are all equivalent. 1. A is invertible. Okay? Now, what this means, if A is invertible, then AX equal B has a unique solution for every B. Okay? Now, of course, if B is the 0 vector of the right size, then the unique solution is 0, 0, 0. Yeah, the X is all 0. But for any other B, there is a unique solution. Make up any B in the world, you do, because A is invertible, and you can do it. Okay? Now, that also means if it is a unique solution, that A has to be. They go both ways. I already included this one, AX equal 0, and that should be the 0 vector. They didn't put it bold. It should be bold.
So is X a vector? Yeah.
X is a vector. Yeah. X1, X2, X3. Yeah. Components to that. This has only, I already said this, the trivial solution. If A is an invertible matrix, that's the only one you can have, because it has a unique solution, and it would have to be 0. So, okay. Another is that A is row equivalent to IN. In other words, that's how we got the inverse, by doing row equivalency. Okay. And 5, the last one then is A can be written as a product of some number of elementary matrices. Okay.
I don't know why, but I was just thinking in my head.
Not just two.
It's not two. But, you think product, like a product.
Yeah. It's a series of products of elementary matrices or something like that. Yeah. Now.
In number of elementary matrices.
Yeah, a number. Yeah. Product of some elementary matrices. Okay. Or a number of elementary matrices. Okay. LU factorization. All right.
Call it Lulu.
Yeah, Lulu. Okay. At the heart of the most efficient and modern algorithms for solving linear equations, AX equal B, is the LU factorization. This is where the practical thing comes, okay?
Thank goodness.
Yes. It doesn't seem like it, but it is, okay? In which a square matrix A is expressed as a product, A is equal to LU, where L is a lower triangular matrix and U is an upper triangular matrix. In this product, the square matrix L is a lower triangular. You remember what that means? Yeah. What about them?
Below the diagonal?
What is? What about it?
Is that the lower triangular?
Yeah.
It's below there. Are they all ones?
No. There are numbers down here and
And
zeros
zeros
above.
Okay,
Yeah.
yes. It's like there's stuff down here and there isn't.
And there's zeros above. Right, exactly. And U is an upper triangular matrix,
So
which
one's
means
all above the diagonal.
not once. Stuff above
Enough,
and the zeros below. Yeah. Now the diagonals,
Can be anything.
yeah, I want to say can be anything, but they aren't zeros. Okay.
Okay, so they also need to be a part of the triangle.
Right. Okay. Yeah.
They're the hypotenuse.
Yeah. Now I'm not saying none of them can be, but I'm thinking that none can be zero.
Yeah, I feel like it would be kind of ambiguous if there was a zero on the.
Anywhere in the diagonal. And the reason is because the next chapter we're going to do determinants of these, and we'll be adding another one down here, maybe another couple down here. And one of them is, we already know that the determinant of A cannot be zero.
If
could have
there's a
already put
zero
that in
on
there.
the thing.
Okay.
it's gonna be-
And if you had a lower or upper, it doesn't matter which, let's say a lower triangular matrix, and these are zeros up here, and you do the determinant, basically your determinant winds up being the product of diagonals. And if one of those is zero, then your determinant is zero, and if your determinant is zero, it's singular, okay, not vertical. So I don't think any of those A's can be zero, okay?
And when it says upper and lower triangle, is it always across this diagonal, or can it be the diagonal? the other
No. It's always upper to lower, upper left to lower right. Yeah,
Just
called the main diagonal.
the main-
Okay. All entries above and all entries below the main diagonal are zero. Yeah. So that leads to the definition of your LU factorization. Okay. Yeah. All right. I think I probably could have written this on that, but I didn't think about it in time. Okay. If the n by n matrix A can be written as the product, and this time it is 2, as the product of a lower
It is two.
triangular matrix and an upper triangular matrix, U, this is the L, this is the U,
upper.
Upper, you got it. Then
Clever name.
A is equal to LU is called the LU factorization of A. Okay. All right. Here's example 5. We're just going to start off by showing you something. And I think I would. Okay. Here's a matrix A. 1, 2, 1, 0. That is a 2. It looks like a 3. Okay. 1, 2, 1, 0. Now, tell me, is that an invertible matrix or not?
Okay, we said, what was the determining factor?
You almost had it. What was the word you just said? The something determining. Sounds like determinant. Yeah. Oh, okay. That's what you're asking.
Yes.
Okay. And what was it?
Can't be 0.
Can't be 0. Is it?
It would be 0 plus 2, which is
Minus 2.
or
Yeah.
minus 2, so
But it's not 0.
It's
Not 0. That's the big thing. So this is, a invertible matrix. Got to be, because it's determinant, it's not 0. And believe it or not, it has a 0 on the diagonal. Okay.
That is surprising.
Yeah. But it's fine. Okay. Now what we need to show, and they're just going to give it to us, that this is 1, 0, 1, 1 multiplied by 1, 2, 0, negative 2. Now they just gave us this out of the blue here, but I can tell you this is a lower triangular matrix. This is a upper. Okay. Now let's see if these two multiply to be that. 1, got it. 1, got it. Say again. Oh, I'm sorry. I went to the wrong one. Yeah.
2, and then down the next
0. That's the 2, and then this is 0. Sure enough, that's a product of those two. One's upper and one's lower triangular matrix. So guess what? That's the LU factorization of that matrix.
So I take it we'll be looking for the LU.
Yeah. So the next thing is how you find them. They gave it to you this time. This is your L times U. Okay?
And then the B is just the same thing with 3 by 3.
What's that?
And then the B part of that is just showing us with a 3 by 3.
Okay. And
I feel like that's just redundant.
I don't know why it took them that many lines to do this. Okay? The B part, is this what you were saying? I couldn't hear. Okay. It's a much bigger one. Okay? Here's your A. Excuse me. I think that's all. I sure hope so.
That's like a sneeze attack.
It was. Major. Okay.
Oh, man.
Wow. I'm not sure I've ever had one that many in a row. I don't know what's happening here. I'm not sure that's going to be the last one either.
Hope they're awake at home.
Yeah. I'm afraid I'm going to bust a blood vessel in my nose or something. All right. Here's an A here. 1, negative 3, 0, 0, 1, 3.
You just really don't want to do this problem.
I must not. 2 minus 10,
You're allergic to this.
2. Sorry. Ah. Sure loosen some stuff up. I wish we had a trash can in here. Get rid of it. I don't know what's happening. I have so little time left, I don't want to run down to the restroom. I may have to, but I'll try not. Okay. Now, again, this is a voila. Here's a lower triangular matrix.
Sneezing out change.
Yes, I know. I must have already lost. I had more. Well, no, I got it. Maybe.
It seems like if you press your tongue against the roof of your mouth, that might help.
Does it?
I want to say I've heard that somewhere.
Well, if you held it up there, there's no way you could sneeze because you got to have the tongue in action, I think, to sneeze. But it's another one coming, I
Give
think.
it a try, yes.
(1-30) (013) 0014. That's certainly a product. It's an upper time, I mean a lower times an upper. Now all that left to do is to show that these two do multiply to be that one. I think we can do that pretty swiftly. 1, 0, 0, that's going to be a 1. You like to go down, so it's going to be a 1, a 0, 0, 0, 0, and that is a 0.
And 2.
2, 0, 0, that's 2. Got it. Next one is a -3 out of B. And
And a 1.
yeah. Okay. 0, 1. So yeah, 1. And then finally
-3, -10.
okay, wait. Which one are you doing now?
The bottom middle one.
This one here?
It's -6 plus.
Yeah, okay, I thought you said -3. Okay. -6 plus -4 is -10. Yeah, -10, got it. And then the last one is the 0, -12 plus 14 is 3. Got it. So yeah, that does multiply with those two. And that's an upper, I mean a lower times an upper. And that is your factorization.
And I think that's time.
And we're out of time, huh?
Just after all that season.
Yeah. Sorry. So anyway, we showed that the linear algebra applied. I'll let you look at that. Computational fluid dynamics uses linear algebra. I'll leave it like that. If that's an interest of yours, that could be a paper topic. Okay? So we'll start next time. Example 6, top of page 80. And I'm
Actually find these.
yeah. Okay. So 2.4 exercises, do any of the odds 1 through 7, either 9 or 11 or both, 13 or 15 or both, 17 or 19, no, any of the odds 17 through 21, either 23 or 25 or both, any of the odds 27 to 33, and then I would think through the true false 35, look at the writing, possibly do 39, and we'll hold off there and pick up there at the end. Oh man, I'm so sorry, we wasted lots of minutes there. And they all got recorded.